AI is starting to show something we used to only guess at, not just whether it can improve, but how fast that improvement follows a measurable curve. That matters because it turns agent learning, optimizer choice, and safety testing into engineering problems with real scaling laws, not one-off demos. The bigger trend here is that frontier systems are becoming more stateful, more adaptive, and much easier to benchmark against the environments they actually operate in. Keep watching, because the details reveal where progress is accelerating, where it breaks, and where the next bottlenecks are hiding. Let's explore the first paper, EdgeBench Unveiling Scaling Laws of Learning from Real-World Environments. EdgeBench from ByteDance Seed introduces a benchmark for studying post-deployment learning in real-world environments, spanning 134 executable tasks across scientific problems and ML, systems and software engineering, combinatorial optimization, professional knowledge work, formal math, and games. Across roughly 38,000 hours of agent interaction, the paper reports that aggregate best so far performance over time follows a highly precise log sigmoid law, S max, et plus te med, te beta, with mean R squared equals 0.998 over the full 134 task average, and R squared is greater than or equal to 0.993, even when extending trajectories to 28 and 72 hours. The same functional form fits each task family, outperforms log probit, log Gompertz, Weibull, and log linear baselines, and can forecast 12-hour performance from only the first 6.5 hours, with R squared is greater than or equal to 0.997 and RMSE below 1. The authors also argue for a frontier expansion mechanism on latent task graphs, where accumulated unlocked capability and remaining locked opportunity drive sigmoid growth in log time. On the model side, learning speed roughly doubles every 3 months across frontier systems, rising by about 8 times from GPT-5 Codex in September 2025 to GPT-5.5 in April 2026. In the 12-hour leaderboard, Claude Opus, 4.8 leads overall with 51.3, followed by GPT-5, 5 at 48.4, and a stateful 12-hour run on the gravitational wave reconstruction task reaches 67 after 247 scored evaluations. Let's explore the second paper, Omniopt Taxonomy, Geometry, and Benchmarking of Modern Optimizers. Omniopt, developed by researchers from Shanghai AI Laboratory, Shanghai University, Westlake University, Shanghai Jiaotong University, UCAS, Zhejiang University, and SUSTech, reframes optimizer design as a mechanism-aware system rather than a flat leaderboard. The paper unifies 108 optimizers with a 5-stage meta pipeline, an LMO-driven 4-axis geometry, and a dual taxonomy that separates method families from effect objectives. In benchmarking 24 representative optimizers, it shows that no single method dominates. On C, for short context pre-training, Apollo reaches the best one B, Perplexity at 13.53, while Muon and Mars Shampoo are close behind at 13.72, yet the cheapest runtime comes from Lion, and the lowest optimizer state memory comes from Adafactor. Across FineWeb Edu 32K long context runs, SOAP is the most stable cross-scenario optimizer, holding the top Perplexity position in 7 of 8 scenarios, while Mars Atom W is the most stable Atom W style enhancement. Apollo is the sharpest cautionary case. It is best at 256 tokens with 13.53 Perplexity, but collapses to 35.4 at 32K, showing that aggressive state compression is rank-bounded and can fail as context length grows. The muon ablation isolates Newton-Schultz orthogonalization as the core gain, recovering Perplexity from 70.74 to 16.86 after removing Atom W-style second moment scaling, and then improving to 13.58 when symmetric learning rate scaling and post-orthogonalization Nesterov are combined at 1B. On CFAR 100, optimizer choice is backbone dependent. Ada Belief leads ResNet 5.0 with 80.53%, Muon leads DITS with 77.38%, and Adan leads CA Former S12 with 84.89%, reinforcing the paper's central claim that optimizer geometry must match model topology and training constraints. Let's explore the third paper, Safety Testing LLM Agents at Scale from Risk Discovery to Evidence-Grounded Verification. VERA, developed by researchers from Ant Group, Zhejiang University, Fudan University, Alibaba Group, Hunan Institute of Advanced Technology, and Deakin University, is an end-to-end safety testing framework for LLM agents that replaces static red teaming with executable safety cases, adaptive multi-turn attacks, and evidence-grounded verification over environment state rather than model self-report. The system continuously mines roughly 800 papers to build taxonomies with 124 risk categories, 77 attack methods, and 30 execution environments, then composes them into 39,078 candidate scenarios, and releases Veribench with 1,600 executable safety cases across 3 threat settings. On 4 production agent frameworks, OpenClaw, Hermes, Codex, and Anthropic's Claude Code 5 ERA, exposes severe weaknesses, with average attack success rates of 90.6% in single-channel testing and 93.9% in multi-channel testing, while overall framework results range from 70.3% for OpenClaw to 88.6% for Claude Code. The benchmark also shows that attackability depends sharply on the interaction between risk, environment, and attack method. For example, integrity averages 95.3% ESR, harm output 79%, and social engineer falls to 42.9% in CRM and SVC. Vera-derived supervision transfers beyond the benchmark, where fine-tuning Qwen3 Guard raises RJudge performance from 59.4% accuracy, 32.3% recall, and 45.8%, F1 to 61.7%, 77.9%, and 68.4%, with a separate run reaching 0.93 accuracy and 0.941 F1, and a best evaluation loss of 0.0387 at step 210. That's a wrap on today's AI paper highlights. Thanks for watching.